Hey everyone, in this section we are taking a look at the first derivative and what it tells us about the original function. So we are going to be thinking graphically quite a bit here. So starting off with if the first derivative is positive. So remember, the first derivative is the slope of the tangent line. So if the slope is positive, let me graph something that might have a positive slope. There's a line with a positive slope. Then we know that this line was increasing. The y values were getting larger. So if the first derivative is greater than 0, then you know that the function is increasing. Whereas if the first derivative is less than 0, that means the slope is negative. So that would be, for example, a line like so. This has a negative slope. So this tells me that the function is decreasing. The y values are getting smaller. So the first derivative is going to tell us whether the original function is increasing or decreasing. So now moving on to the first derivative test, since the first derivative tells us whether the function increases or decreases, then it's also going to help us find local maxes and local mins. So I'm actually going to start with a drawing here in this first box of the function. So let's draw a function that looks like this. Something that might be, let's say, like part of a parabola that opens down, or it could be part of a polynomial, a portion of the polynomial that is opening down like this. So if you take a look at the slope, notice what's happening. The slope goes from positive, and then the slope changes to negative. We're talking about the slope of the tangent lines. And where the slope changes would be this point here. We're going to mark that point as C. So we're talking about this value C. This is a critical point or a critical number. Remember, a critical number is either where the derivative is equal to 0 or the derivative doesn't exist. So if we have a critical number and the graph is changing from increasing to decreasing, that means that the derivative is changing from positive to negative. Then that means that our function f of x must have had a local maximum at C. So if the derivative changes from positive to negative, we have a local max at C. So let's take a look at what that looks like if we analyze just the first derivative itself. So if we're only looking at the first derivative values, and this is what our test will really look like in a little bit when we do an example. If we have our critical number, and then we take a look at the first derivative values around the critical number, if the first derivative changes from positive values to negative values, then we're guaranteed that we had a local max at C. Now let's look at the reverse situation. So if the first derivative is going to change from negative to positive, that means that the graph went from decreasing and then changed to increasing. So now we have our critical number there, or critical value, which again we're calling C. So my critical number is C. So now my graph is going from decreasing and then changing to increasing, which means the derivative is changing from negative to positive. And that tells me that the graph of the function has a local minimum at C, a local min. So if we are to analyze just the derivative values here, we look at just the derivative values around C in this case, if the function went from decreasing, that meant the first derivative, the slope was negative, and then if it changes to increasing, then the first derivative or the slope is positive. So when the first derivative changes from negative to positive, that means that we have a local minimum. And then the last case is, what if there is no change in sign? What might that look like? What if the first derivative doesn't change sign at all? So for example, what if your graph, your function, it was increasing and then it went to a slope of 0 and then it continued to increase? So something like this. This might be like a cubic graph. So we still have a critical number. We have a point where the slope is equal to 0, but notice the graph is increasing the whole time. The derivative never changes sign. So looking around that critical number, in this case, the way I have my graph drawn, my slope is positive, and then my slope continues to be positive. So that means that there is no change in sign. If the derivative does not change sign at c, then that means that there will not be a max or a min. So we have no max or min at c. And later on, we'll talk about how in this particular graph, the one that I have drawn, it turns out that that is an inflection point. But we'll talk about that later when we talk about concavity. So in this section, we are going to be focusing on the first derivative. We're going to analyze the first derivative and use our analysis to figure out information about the original function. So we're not going to be trying to graph the original function, but rather use the derivative to give us information about the original function. And since the derivative is the slope, then we know that the derivative is going to give us key information about whether the function is increasing or decreasing, which then will lead to information about whether we have a local maximum or a local minimum. So for example 1, we have the function f of x equals 2/3 x to the third power plus 5/2 x squared minus 3x plus 6. And we are looking to determine any local maximum or minimum values, as well as the intervals where the function is increasing or decreasing. So I like to start with the domain. This is a polynomial function, so we can have any values for x, so therefore the domain is all real numbers. And anytime you're asked to find local maxes or mins, we're going to rely on that first derivative test. So we're going to compute the first derivative, and we're going to find our critical numbers first. So the derivative of 2/3 x cubed, remember the 2/3 is a coefficient, and then we'll multiply that by the derivative of x cubed, which is 3x squared, plus 5/2 is my coefficient. The derivative of x squared is 2x. And then the derivative of negative 3x is just a negative 3. And the derivative of 6, since it's a constant, is 0. So if we simplify, we'll end up with 2x squared plus 5x minus 3 for my derivative. Now to find critical numbers, remember we're going to branch off and we're going to do two different things. We're going to find where the derivative is equal to 0 or where the derivative is undefined. So I'm going to set this derivative equal to 0. 2x squared plus 5x minus 3 is equal to 0, and solve this equation. So since this is a quadratic, a polynomial, I'm going to go ahead and try to factor it. And then if it doesn't factor, we can use the quadratic formula. So it looks like this is going to factor into 2x minus 1 times x plus 3 is equal to 0. So we have x equals 1/2 and x equals negative 3 for starters, and these are my critical numbers. Remember, critical numbers or critical values, those are interchangeable. Now, will this derivative ever be undefined? 2x squared plus 5x minus 3, it has a domain of all real numbers, so it is never undefined. So I'm just going to write never here so that I recognize that I did think about it. The derivative is never undefined. So I have my critical numbers. These are where the derivative is equal to 0, which means this is where we have a horizontal tangent. However, we don't know if these are going to give us local maximums or minimums until we do the first derivative test. So for the first derivative test, I like to label my number line with an F prime as a reminder that I'm doing the first derivative test here. I'm going to test around my critical numbers, negative 3 and 1/2. And then I'm going to go ahead and test values smaller than negative 3, maybe negative 4, something between negative 3 and 1/2, how about 0, and something bigger than 1/2, how about positive 1. And then remember, if you're choosing to test, it is usually most helpful to test back into your factored form. So the factored form was 2x minus 1 times x plus 3. So I'm essentially multiplying 2 times negative 4 minus 1, and then substituting in negative 4 plus 3, and then thinking about whether this will yield a positive or a negative answer. So I'm not really so concerned about the actual computation, but just keeping track of my negatives and my positives. So 2 times negative 4 is negative 8, minus 1 is negative 9, so that's a negative. And negative 4 plus 3 is also a negative. So I really end up with a negative times a negative, which overall results in a positive. So I put a plus sign on my number line here to indicate that I will end up getting positive first derivatives, positive outputs, when I put in values that are smaller than negative 3. So now we'll test 0. So same thing, 2 times 0 minus 1 times 0 plus 3. So that's going to end up yielding a negative value times a positive value, which will overall be negative. So I end up with the negative values between negative 3 and 1/2. Those result in negative first derivatives. And let me mention that it is completely fine if you're doing this testing in your head and you're not actually writing down the computation. Just be careful so we're not making any silly mistakes. So now substitute in 1. 2 times 1 minus 1 times 1 plus 3. So that'll yield a positive times another positive, which is overall positive. Therefore, I have a positive here as well. So that's using testing to determine the signs of the first derivative. But let me also mention you have a graphical way of tackling a problem like this as well. This is an alternative to testing because we should know the shape of this particular first derivative. 2x squared plus 5x minus 3 is going to be a parabola. So we essentially have a parabola that opens up. So you could technically bypass all of this testing if you think graphically, which is usually my preference because it's less work. And we know where the parabola is above the x-axis, that corresponds to positive y values, and where it's below the x-axis, that corresponds to negative y values. So you could certainly rely on the graph to do this analysis rather than testing points. So now let's go back to what this means in terms of increasing and decreasing for the original function. So if my first derivative is positive, remember this is telling me that my function is increasing, and then it changes to decreasing when the derivative is negative, and then it changes back to increasing again when the derivative is positive. So if you are to graph something like that, if a graph goes from, let's say the graph goes from positive slope, meaning it's increasing, and then it changes to a negative slope, which means it's decreasing, then that means we have reached a point which is going to be a local max. So this is telling us that we are going to have a maximum, at negative 3. Whereas at 1/2, the derivative goes from negative to positive. So the slope is going from negative to positive. So the graph is going from decreasing to increasing, which means we have a local minimum. So the sign of the first derivative is helping us to figure out whether the graph has a maximum or a minimum. So now we can go back and answer all of the questions that we were asked for. It said we wanted to find the local max and local minimum values, as well as where the function is increasing and where the function is decreasing. So let's start out with the increasing intervals. I'll just write INC for increasing. The increasing intervals are where the first derivative is positive. So that's negative infinity to negative 3, and again from 1/2 to infinity. The original function will then decrease where the first derivative is negative, which would be from negative 3 to positive 1/2. And now we're going to go ahead and find our local max value. And notice the word value. Let me go back up. When it asks you specifically for a value here, a value implies that it's asking you for the y value. So when they ask for the local max value, they're not so much interested in the ordered pair, but actually the y value. So we identified that we have a local max here when x equals -3. So you'll need to plug -3 into the original function, which means you're going to find f of -3. And that y value is your local max value. So this is where you would pause the video and go back, grab your calculator, take this original function, and let's go ahead and substitute in -3 using your calculator and get the y value. Then come back to me and let's verify. Really important that you're using your calculator so we don't make any silly calculator keystroke mistakes. So I'm getting a y value of exactly 19.5. So then my local max value is going to be 19.5. And then my local minimum value, if I take a look back at my first derivative test, we said that the minimum is going to occur when x equals 1/2. So we need to go ahead and substitute in 1/2 into our function. So let's compute f of 1/2. Again, pause, use your calculator. This one is going to be an approximate. And I'm getting that is approximately 5.21. So that would be my local minimum value. And then I always recommend that you go to your graphing calculator or perhaps Desmos and take a look. I'm going to show you pulling up Desmos to see if on the graph, if this looks pretty good. So if you grab your graphing calculator or open up Desmos, let's go ahead and put the original function in to Desmos. So I've got my function in here in Desmos, and I'm going to go ahead and pinch and zoom out so I can see the entire function. And I just want to check the basic shape and see if it matches what we just came up with. So we said that the graph was increasing from -infinity to -3. So sure enough, if we look at this cubic curve, it's increasing here from -infinity, and it does indeed look like this point here, that maximum there, is occurring at -3. And then it looks like our graph decreases from -3 here to approximately, on this graph, 1/2, and that aligns with what we thought, that this minimum here, local minimum, occurred at approximately x equals 1/2. And then the graph does indeed appear to increase the rest of the way from +1/2 to infinity. So the graph supports all of our algebraic work, and it's always a good idea to check with your graph at the very end.